And I'm back. And I'm back. And here I begin again with linear inequalities in Paul's online notes. So we'll start out just with solving linear inequalities. And I must open this twice because it has that bug in it, which tells me to open it twice. Linear inequalities. And thus we commence. Give the solution in both inequality and interval notations, huh? All right, so just the first 4 to start us off with. So I shall expand on the left and on the right. For z, take plus 8, take 1 is greater than 5, take 28, plus 7z. And now I shall bring all z terms to one side. So it becomes negative 3z. That there is a plus 7. And I shall bring it to the other side. To be minus 7. And then I shall compute this. So 5 minus 28 is minus 23. Minus 23 minus 7 is minus 30. So minus 3z is greater than minus 30. Now divide both sides by negative 3. And do not forget to invert the sign or flip it. And we get that 10 is less, z is less than 10. That is in inequality notation. But we also want interval notation. So I declare something along these lines. Negative infinity, comma, 10. Now, I can't include negative infinity like by definition, so that has to be a rounded bracket. And for this one, do I do a rounded bracket or a square bracket? Well, I don't include 10, so it should be a rounded bracket. So this is how some people express it using interval notation. Some people do this, like that. But it's if it's obvious, you don't have to include that, I believe. And so now we must check. We must check. Everything must be checked. Okay, so he does not declare that Z is a member of that interval, that infinite set. All right, so that was successfully done. And now we try the next problem. So we shall expand the brackets, shall we? No, that's not good. Instead, I mean, who wants to work with all these fractions? Not me. So I'm going to multiply both sides by 4. By 4? By 4. Nothing will, it will still remain the inequality that it is. So if I multiply that by 4, the half turns into 2. And if I multiply this by 4, the 6 turns into 24. And if I multiply this by 4, it just turns into good old negative 1. And now to expand. So I will have 6 plus 8t on the left. And what is a third of 24? Well, that would be 8. And what is half of 24? That would be 12. So I write negative 12t. And now I've got this minus sign in front of a bracket. So it becomes minus 2 minus 10t. And now this is much simpler. Minus 12t minus 10t is minus 22t. And add that onto the left, and you'll get 30t over here. 8 minus 2 is 6. But we've got to take away 6 from both sides, so it'll be 0. So 30t is less than or equal to 0. So t itself, dividing both sides by 30, is less than 0. And that there is inequality notation. But you also want interval notation. So what you should do is do minus infinity on the left with a round bracket, and 0 with a square bracket on the right, because you have to include the 0, you know? And we must check. Everything must be checked. And that is correct. That is correct. Next, we have a compound inequality, or like a 3-part inequality, if you know what I mean. Okay, that's the third problem. So what do I do? What do I do? First, I shall take away 2 from the left piece, the middle piece, and the right piece. Or the left side, the middle side, and the right side, as some people call it. Okay, that gives me negative 3 on the left, 4x in the middle, like I intended, and 8 on the right. And now I will divide the left and the middle and the right by 4. That traps x in the middle, just like that. So that's interval, that's inequality notation, but you want interval notation as well, right? So put negative 3/4 on the left and a comma, and 2 on the right, and put them in a pair of round brackets, because you do not include those 2 end numbers. And there you go. We will check it once we've solved problem 4. So we're going to immediately start by subtracting 3 from the left and the middle and the right. So we're going to have 5 is less than or equal to negative 5z, which is less than 9. And then we're going to divide the left and the middle and the right by negative 5. So we get negative 1 on the left and negative 9/5 on the right. And good old just regular z in the middle. Now, wait a minute. Negative 9/5, isn't that less than negative 1? It is. So it would, to be logical, like these would have to flip. Now we understand why they flip instead of just memorizing why. So that's inequality notation right there for you. But you also want set interval notation. So put -1 on the left. Actually, reconsider a little bit. Hold on, just a minute now. Just a minute now. If I were to do this, this is actually wrong because you have to put the lesser number on the left. Okay, so it should be the other way around. Like this. And then you have to ask yourself, do I include -1? Yes, I do, so square bracket. Do I include -9/5? No, I don't, so round bracket. And let's put a green bow around it. Why not? Bow and box, they have similar letters. Okay, so that is, and this one is valid. That is correct. But notice they flipped it round. And they say that it's more quote-unquote standard form. They don't say that it has to be done, but they just say it's like more standard. Just like when you say x, y equals blah, 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 instead of putting y on the right-hand side, they put it on the left. But here, I think you actually have to do it, right? Okay. Oh, yes, look at that. It's always on the left. Okay? So to be totally clear, this is preferred for inequality notation. Whereas the green one is mandatory. And now comes the next three inequalities to solve. For number 5, I will add 15 to the left and the middle and the right. So I get 15 on the left, 10W in the middle, and 38 on the right. Okay. Then I would divide the left and the middle and the right by 10 to get 1.5 on the left, W in the middle, and 3.8 on the right, which is all fine and well for interval notation. And what about set notation? Well, just write 1.5, comma, 3.8, square brackets on both sides, and you're good. That's good. For the sixth one here, first subtract 1/6 from the left and the middle and the right. So we're going to get 11/6 on the left, minus half x in the middle, and 3 5/6 on the right, which is 23/6. And now multiply the left and the middle and the right by -2. By -2. So that will turn the left into 11/3 and the right into 23/3. But hold on now. What about the signs? Minus there, minus there. Okay, and good old x in the middle. So it'll be like that. But we remember from last time, they want the lesser number on the left to be more quote-unquote standard form. So we shall oblige and do that. So here it is. Here you go. And that is inequality form. And now for interval notation. Negative 23 over 3 here, comma. Negative 11 over 3 here. And round brackets on the right and square brackets on the left. Because we include him and exclude him. I don't know why I'm saying him, but whatever. Now comes problem 7. If 0 is less than or equal to x, which is less than 3, determine A and B for the inequality that you see right here. So what I shall do is I shall first multiply the left and the middle and the right by 4. That's what I will do. So we're going to get, this is going to turn into 0, 4x, and 12. And now I shall add 1 to the left and the middle and the right. So 1 there, 4x plus 1 there, and 13, hold on, and 13 there. Thus, A is 1 and B is 13. And now we check. Everything must be checked. Okay, so they've decided to use rational numbers, and that's fine. These are equivalent decimals. And then this is valid. And so is this. All correct. Good. And last, indeed, this agrees with us. So we save our work. Stop, please. And we begin again. Not the exact same thing again, because that would not be interesting to me. We do polynomial inequalities. Okay. Polynomial inequalities. Okay. I will title the work Polynomial Inequalities. And now we will commence. We will start. Solve the following inequalities. I would do the first 3. Okay, hold on. I'm going to subtract 21 from both sides. So I will get u squared add 4u, take 21 is greater than or equal to 0. And then I notice this can be factorized into u plus 7 times u minus 3. Now, visually, I'm picturing a quadratic graph, a classic U-shape or parabola shape, which cuts through the x-axis at -7 and 3, right? That's what I'm picturing in my mind. And how does that help me? Well, I have to consider when u plus 7 times u minus 3 is greater than or equal to 0. Not equal to 0, but greater than or equal to 0. And here's the thing about that. So basically, like, what does that mean? That means it will be like either like there's 3 parts of the number line now, the left and the middle and the right. And we have to, choose which one is actually appropriate. Okay, so if I stick in 0, well, then I get 0 plus 7 times 0 minus 3, which is minus 21. Is minus 21 greater than or equal to 0? No, it is not. And so the middle of the number line is excluded because I tested 0, who is in that region, and it doesn't work. Now test out what happens if you put in, I don't know, 5. You put in 5 and you get what? 12 times 2, which is 24, which works. And if you put in minus 10, well, then you get minus 3 times minus 13, and you get 39, which is indeed greater than or equal to 0. Okay, so that's the logic. And so our conclusion is that u is less than or equal to -7 or greater than or equal to 3. And now we shall check. And you see that we are correct. But they also want interval notation, I guess. So if you wish, I will put this here. They've used the word and I dislike that. And I will use that, and that is good. Next comes problem 2. So I can factorize this. I can. X plus 6 times x plus 2 is less than 0. So on the number line, we have it cutting through -6 and -2. Okay. So you test values from all 3 regions. So here, let's test the number -3. I will get 3 times -1. And is that less than 0? It is indeed. So the middle region works. By the way, this actually means and implies that the other 2 regions won't. But when you're just starting out, test your regions, right? If I put in 0, of course it doesn't work. So this side is a failure. And if I put in -10, of course it doesn't work. In fact, if you think about it, just put in like negative a million, right? Because this will be some giant negative number, some giant negative number. You multiply them and you get a giant positive number, and that is not less than 0. So this region here does not work. You don't have to use a specific number. Okay, so what do we conclude? We conclude that Z is pinced between -6 and -2, or in interval notation, just like that. And now we shall handle problem 3. We shall handle problem 3. Here it comes. Let's move everything over to the left. So we get 4t squared plus 17t minus 15 is less than or equal to 0. So what do you think about that? Well, I think that can be factored. Oh, really? Why don't you show me? Okay, I'll put a pair of brackets, and I'll put t there and 4t there, and I'll add 5 and take away 3. How about that? Okay, this is good. This is good. So we, pretending in our minds that it's an equation, we get 3/4 and -5. Those are like our special numbers. So we picture our number line, and we have -5 there and 3/4 there. Now, what did I say? I say test your regions. Test your regions. So who's between here? Who is very, very, very convenient? The answer is 0. 0. You stick in 0, and what do you get? You get -3 times 5, which is -15, which is indeed less than or equal to 0. So the middle region is valid. This implies the other two regions are invalid, but here I'll run through the reasoning once more. Over here, just stick in two massive positive numbers. You multiply them, you get another massive positive number, which will be a failure. Here, stick in two massive negative numbers. You multiply them, you'll get a number that's bigger than 0, so it's a failure. And there you go. Conclusion, t is trapped between -5 and 3/4. Interval notation, please. -5 on the left, comma, 3/4 on the right, square brackets on both sides. And now to check. Everything must be checked. Forever and ever. Check, check, check. Okay, that is correct. Next one. That is correct. Problem 4, 5, and 6. Here we go. For problem 4, I subtract 12z. And you know what? It is no longer factorizable because I have 34, which is a product of 2 and 17, which you cannot make a 12 from that. So you must resort to the formula. The formula, no? What formula do you mean? Well, I mean this one. Z is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. What? 1 second. It has just occurred to me. Oh my goodness me! Look at that. I can have plain paper. Well, I'm just in paradise. I didn't know that. Hooray! Whoa. Okay. I don't know if I want yellow. I know this is not relevant, but I just, I have to try some of this stuff. Blue paper. Wow. Oh my god. Okay. No, I'm not going to be like absolutely everybody and use black paper for everything. Okay. It's going to be plain, and I'm not going to make it blue. Because, all right. We'll just try this out just so that the lines are not in the way. Okay. So, So I apply this. So here is my value for b. It is -12, and that must be made negative. So it becomes 12 itself. Plus or minus the square of -12, which is 144, minus 4 times 1 times 34. Now, what is 4 times 34? The answer is 136. And 144 take 136 is 8. And so all of this is divided by 2, by the way, because a is 1. So z is equal to 12 plus or minus the square root of 8, which is 2 root 2. 2 root 2. And all of that is divided by 2. So 6 plus or minus the square root of 2. 6 plus or minus the square root of 2. What does that look like on a number line? Well, it looks like this, where you have 6 bang in the middle, 6 plus root 2 over here, and 6 minus root 2 over there. So what am I supposed to check? What am I supposed to check? Well, if you stick in an extremely large positive number, okay, when you square it, that will just crush everything else. It's minus 12. Z, it doesn't matter because you squared a billion, trillion. Okay, so, and then this 34 that you add on the end doesn't matter at all. So you have a massive number which is greater than 0, and so this region over here is a success. It works. Stick in a massive negative number, and then you have a massive negative number squared, which is positive. And the other two terms basically don't matter at that point. So this region over here, shooting off to the negatives, that's a success. But the region in the middle is a failure. And if you don't believe me, stick in the number 6. You'll see it doesn't work. 6 squared takes 72, add 34. Is that greater than 0? No. Okay, so what's the answer then? What is the actual answer? The answer is 6 minus root 2 and z. Oh, hold on. 1 second. Z is less than 6 minus root 2, or z is greater than 6 plus root 2. And you want interval notation? Okay, negative infinity, 6 minus root 2, or 6 plus root 2, comma, positive infinity, and that solves it. Now for problem 5. We will check the answer to this one momentarily. Okay, so I have y squared minus 2y plus 1. That is a perfect square. It is y minus 1 squared. So the roots to this, treating it as an equation in our minds, it has a double root, which is 1. Just 1. So what does one do? What does one do in that situation? Right? Okay, you test. You test the region on the right, and you test the region on the left. But then you think to yourself, wait a minute. Wait. So I'm squaring something. And according to this, I get a number that is less than 0. Such a thing does not exist. That's never true. Unless y is actually equal to 1 itself. That's the only condition. The only condition by which that is true. Everywhere else is a failure. So we simply say y is equal to 1. I think that's how you answer it. What we're about to see, I guess. And in interval notation, I guess I could try this out. We'll see. We will see. In fact, we'll check and verify right now. So for problem 4, we end up with this. Okay, so they decided to decimalize the answer. That is 6 plus the square root of 2, and that is 6 minus the square root of 2. So that is valid. But problem 5 is what we're interested in. Look at that. Y is equal to 1. But there is no interval notation. You know, I think people would be okay with this, but it's not standard. Maybe it's called a point interval. That would be logical. Okay, now problem 6. Problem 6. Here we go. Okay, all right. So factor out t squared, why not? And then you have t squared plus t minus 12 is less than 0, just like that. Okay, factor this into t plus 4 times t minus 3. And now think carefully what this is telling you. Well, this is a quartic, a polynomial. And it is telling me that 0, negative 4, and positive 3 are special. So -4 is like there, and 0 is like there, and 3 is there. And because it is t to the 4, it is an even degree polynomial, so it has, roughly speaking, a U-shape like that. If you feed in negative infinity and positive infinity, you get the end behavior, which is, you know, quadratics and quartics and sextics. They all behave like they have a U-shape. Anyway, what does this mean? Okay, so it's going to go through there, but then what? It'll touch it there and do that. Right? Right. So now to determine which regions are included and which are not. Which are included and which are not. Okay? So I believe it's the two middle ones. But we're about to see. We're about to see. So if I stick in a extremely huge positive number into this, t to the 4 just crushes t cubed and negative t 12 t squared, and they don't matter anymore. And then I've got a massive positive number less than 0. No, that's not true. So that region there is excluded. Same logic for a massive negative number, and that region there is excluded. But what about the two middle ones? I think they are valid, but you have to check. You have to check. Okay, so just put in the number 1. 1 squared times 5 times -2. That gives you -10. So this region passes. Then stick in -1. That becomes 1. That becomes 3. And that becomes -4. And you multiply them together, and that passes. So that's good. So now to efficiently describe it. Notice this is very, very, very important. 0 itself is excluded, and 3 itself is excluded, and -4 itself is excluded. That's very important, because it's so tempting to just say, oh, I know, it's all of this. No, it's not. That right there is excluded. So now to do interval notation. All right, so here we go. Answer. -4, 0, t in the middle, signs like that. And 0, 3, t in the middle, signs like that. And now they want interval notation as well. So -4 on the left, comma, 0 on the right, and round brackets on both sides, because I do not include -4 and I do not include 0. Same story over here. And now we check. We must check everything. And that is correct, and that is good. It's good to be correct. So save as polynomial inequalities and begin again. Okay. Hold on. Let me title my work and let me find out what my work is. Rational inequalities comes next. Oh, look at that. Absolute value equations. That will be interesting. Okay, so rational inequalities is next. And this is pretty interesting. You can sort of toggle between plain and lined. Okay, I will begin. Problem 1. So, what do you do? Well, if you multiply both sides by x plus 3, surely that is fully. Let's just try to do it ourselves. So note, x cannot be equal to -3, because then we would have 0 in the denominator. And that truth must hold forever throughout the whole thing. So we will try. So let's think. Okay, so if I just do this, I want to see what happens. So what? 4 is greater than x? Or rather, x is less than 4. Okay, so I'm tempted to deliver this as my final answer. But I'm nervous about doing that. But nonetheless, I'm curious. I'm curious to see what happens. Okay, that is completely and utterly garbage. All right, so I must really understand what the heck this is even saying. I see. So think a little bit more critically about this. Don't just say the first thing that you think. Okay. Let's think. So this has to be bigger than 0. So I've got one thing divided by another, and the answer I get is positive. The only way that can happen is with positive over positive or negative over negative. Okay, case 1. This, positive over positive. Yeah. So this and this. And when is this true at the same time? Well, it's true when 4 is greater than x and x is greater than -3. So there. And we try a number, like stick in the number 0, and you can clearly see that that works. Okay, case 2 would be negative. You know what? Here's something. Here's how you can actually abbreviate the word positive. Just say that. Positive plus sign VE. That means positive. Like that. Okay, case 2 is negative over negative. Okay, fine. 4 take x is less than 0, and x plus 3 is less than 0. So what you're saying is that x is greater than 4, and at the same time less than negative 3. Impossible. Impossible. So I think that's the answer. And we check. Well, we have to wait, I guess. Okay, while it's taking a century to load a completely static web page, let's put up number 2. Oh, here we go. Oh, yes, look at that. Okay, that's tremendous. Interval notation, don't forget that. Fine. Problem number 2. Problem number 2. This is less than or equal to 0. And the only way that can happen is plus over minus or minus over plus. Right? So, case 1. And, oh no, did you see that? It has less than or equal to. You trickster. So, we'll put greater than or equal to 0, just like that. And on the bottom, z minus 7 is, wait for it, less than 0. It cannot be equal to 0 because it's on denominator, right? I hope I didn't make that mistake of saying that disgraceful thing up here, and I didn't, thank goodness. You never want to divide by 0. Okay, so is this possible? Okay, that would say 2z. Well, can I just cut to the chase? This would say z is greater than or equal to 5 over 2. And at the same time, z is less than 7. Is that possible? Yes, it is. Just like that. Interval notation, comma, round bracket. Case 2, or case B, is that 2z minus 5 is less than or equal to 0, and z minus 7 is greater than 0. So z is less than or equal to what? 5 over 2, and z is greater than 7. Now, obviously, that can't be true, so I hope you're seeing a pattern here. Yes, once you've explored that, this one basically comes for free, I believe. But he's always going to teach me something. Okay, that is valid and that is good. Okay, problem 3. Problem 3. A quadratic divided by a linear. What do I do? Well, I'll factorize the top. To have w at 6 times w take 1. And w take 3 on the bottom. And that is greater than or equal to 0. And now, when is that positive? Non-negative. It's non-negative when the top is greater than 0 and the bottom is greater than 0. Okay. These both have to be true at the exact same time. So we say w is greater than or equal to 3. We'll put in interval notation. 3, infinity, just like that. Case 2 is the negative over negative situation. So when w at 6 times w take 1 is less than or equal to 0, which happens betwixt here. And the other situation is when w take 3 is less than or equal to 0. So w is less than or equal to 3. So the only time both of those are exactly true and equal is when w is trapped between 1 and negative 6. Right? So we have these two situations. Okay, good. We are correct. And now problem 4. Okay. So in this case, because I don't have 0 on the right-hand side, I'm gonna be risky, and I'm gonna multiply both sides by x minus 1. How about that? Just want to see what happens. Just want to see what happens, because I really do think that 0 is like special. Okay, so I get this. So what do you think? I don't trust it. We'll see. I know it's not going to be this simple. Do you know what? I'm gonna call his bluff. I'm going to call your bluff. You've made it too simple. Yeah, right. I'm sure it's that easy. Okay, so let's do it the real way. Add 2 to both sides. And you shall get that, which becomes that. Oh, I see. So that was just totally rubbish. See? I knew it. I knew that couldn't be the case. So anyway, how is this possible? Well, if you have a positive over a negative, that's situation 1. Whoops. That's positive. And that's negative. Okay, so we have like x trapped between negative 6/5 and 1. We know that. And here's the other situation. You already know this ain't gonna work. But to be thorough. Can this be true at the same time? Of course, impossible. So I claim this is the final and real answer. This one right here. Not that one. See? Got it. There's nothing better than getting it correct. Okay, problem 5. Problem 5. This time, u is less than or equal to 4 over u take 3. We are tempted to do this business. Oh, I know, u squared, you know. and then move it over and say, oh, look, it's an inequality like this. And do this and say, this, right? But is this accurate? We will see if we try way 2, which is to take away u from the right-hand side and see what happens. Like that. And oh gosh. Okay, it's totally valid for me to multiply both sides by -1, is it not? And for me to just solve this inequality. And now, situation 1. Positive over positive. Here we go, here we go, here we go. I have no, wrong indeed. Indeed. Situation 1 is positive over negative. Don't you know? So, on the top, if I want that quadratic to be positive, well then u would have to be less than or equal to -1. Or greater than or equal to 4. And if I want that to be negative, u take 3 would have to be less than 0. U take 3 would have to be less than 0, so u would have to be less than 3. So how can these both be true at the exact same time? The answer is that u has to be less than 3. It's the only way. It's the only way. Situation 2 is this one. So how is that possible? Over that. Okay, so when is that actually possible? That's when it's possible. To put it another way, I mean, I don't want to use interval notation. I just want to think about this. So either that or that. So we say that. But I have to check. I mean, look, I mean, I just reject this straight away. This is just obviously false. Or is it obviously false? Or is it? You know, these problems are not they're not here to be that. Oh, darn it! How? Okay, so this up here must be wrong, and I just don't see why it's wrong. Okay, so okay. Okay, so we're in agreement that that's what you do. Okay, we're in agreement up to here. Up to here, we're in agreement. Aren't we? Yes, we are. We're in agreement. That the rational expression can only change sign when the numerator is 0 and or negative 1, 4. Okay, No! No, 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 no. Look what I didn't realize. This is positive 3. So this should be negative 1. How frustrating. How frustrating. But you live and you learn. And I'm only human. So negative 1 there and negative 1 there. Had I only seen that, it would have been okay. You know, it's what can you do? Problem numero 6. Problem number 6. Number 6. And then I want to get up and stretch my legs. I mean, look how long this is taking to load. Oh, wait, we don't actually need it to solve it. Okay, so on the numerator, factor out t squared, yes. And we get t minus 6. And on the denominator, t minus 2. All right. And then the question is, when is that greater than 0? It's greater than 0 when they're both positive or both negative on the So that is the case when t is the numerator is positive when t is greater than 6. And the denominator is positive when t is greater than 2. Hold on. Did I just write that? It has to be 6. And when are they both true? Situation 2 is negative over negative. And when is that true? When do you get a negative on the numerator? I have a feeling that this is going to be packed with booby traps. Okay. Oh, for goodness. Okay. When is the top negative? When that will always be positive, so I don't even have to worry about that. It's just whenever t minus 6 is negative, which is when t is less than 6. Quite simply. And that's negative when t is less than 2. And when are these both true? So is that it? This, right? Oh, goodness me. It's going to be full of traps, isn't it? Oh, my goodness me. I knew it couldn't be that easy. It just couldn't. It just could not be that easy. All right, I give in. I want to know when. Think carefully. It's not true when t is 0 itself, but why? But why? But why is that not true? What? Oh my goodness me, because it turns into 0. You must exclude 0. You must exclude 0. Look, the greater than sign is very, very, very important. I'm learning a lot right now. It's true. Here's the reality. Gotta look out for those special values. See? I love these. These are such well-designed exercises. I can't commend him enough. Recommend him enough. Hey, wait, commend? Recommend. Maybe there's a action there. All right. In the collection. But first, I've got to stretch my legs. Be well, be well.